Morning, everybody. Today we'll see some problems on one problem on switches and two problems on. So you started talking about writing in the lectures, right? All right. So quickly down the first. It's a very short problem, but I forgot to print the. So I need to write it down. So today is. Okay, the first problem is time, space, time switches. Problem number 1. And very quickly, we want to design a TST switch with 2048 channels. To design a time, space, time with 2048 channels organized in 16 TDM lines, 8 bits long, that's given, and the probability a time switch is occupied is equal to 0.1. The overall probability of blocking should be or should not exceed 0.0. And want to design the switch and calculate its overall complexity. Okay, sorry for the writing, but it's better we have it over here. So you remember time, space, time switches, right? So we have this from the lectures, and we're going to use this diagram. So what we want to calculate is the only constraint is probability, blocking probability. We want to transform this or to express that in terms of some parameters of the switch, right? For what parameter we are good to go with this probability of blocking probability. Let's go back to what we know. For first of all, what is given? We have 16 TDM lines, right? So N 16. Perfect. TDM lines. What about N small? Is it? N is, we have 2 lines, channels, and we organize them in lines. And each line is 8 bits long. So we need to break the 2004 into what? Right? 2048 divided by 16, and we get the number of channels that each TDM line will have, right? Okay. So that's a small is expressed over here. So we have how many slots here, right? Because this is a time. So at the input we have 128 slots. What tells the probability of blocking to be maximum 0.002. So do you remember the probability of blocking for a switch of that form? Perfect, yes. So midterm helped a lot, eh? Okay, so Let's quickly deal with blocking is equal, for that I can write it down, I mean it's the same thing, but anyway, of all paths are busy, that's standard thing, right? And this is equal to probability dependence and arbitrary busy to what? Power of k, right? Where k is what? K is the number of slots, right? So k is slots over here, all right. And then what else we have? This is equal to at least one, right? Yeah. One line in a path is busy. To the power of k, and then this is equal to two independent components, both should be down, or basically no, 1 minus both is this probability over here. 1 minus p prime, and we'll define that square to the power of k. Okay, where is equal to what? np. If you remember, we define it as p over n over k. There are many ways to visualize that. I guess you are comfortable with this. Okay, so what we want from this is to be at most. So this at most makes us feel that, okay, I'm going to take it to make my life easier because I have to pay for something, right? There is no way it's going to be zero. So P blocking is equal to 1 minus 1 over k square over the power of k equals to 0.02. So we won't do it now. You can do it in many ways, even trial and error too. And k approximately equal to 25. So that's what? That's the desirable number of slots in time switch over here. This is k, right? In order to satisfy this probability of blocking constraint. So with that said, now we have what? We know the switch looks like, we know k, we know n, we know all the values, so we can draw it. Since we know all the parameters. Okay, now the complexity. For the complexity, if you are familiar, you can again use the formulas, otherwise we can quickly go over it. And what's the complexity? So how do we express complexity in switches? And for complexity equals number of points plus of memory bits, right? Data and control divided by 100 usually. Memory is cheaper, you know, they wanted to lower it down, okay. Plus number of control data. I hope it's clear. Okay, that's a formula. Now let's go and calculate each one of these. Number of cross points is equal to what? N lines, right? Perfect. Is equal to n squared, which is 16 to 256. Then what else do we have? Yeah, bits, let's say bits in the data memory of the time switches, right? Number of bits in the data memory of time switch we represent it as TS. Okay, so what? We are here of memory bits. So we want, basically, we store it to the memory, right? So we have n slots. Each one of those has length what? 8 bits, L. How many switches do we have? 2n. So this complexity is equal to, n, yeah, that's fine, times n times L. Where L, I'm going to write it over here, is length of a slot equals 8 bits. So this gives 2 times 16 times 128, 8, and at the end it's 32,768. Okay. Then what else? Number of bits.
28 total of n and n, because if k is 25, then k. So like
If n,
28 like is small n into l. So 128 is
here,
yeah, and each one is 8 bits.
right, the total number of slots.
Yeah, number of slots. So it should be by 8.
No, because the number of bits is number of slots times slot size, right? The total number of bits for this input. So why it's divided?
Because generally k should be more than small n.
Yeah, it's not, yeah. Okay, so we all agree with what we said over here, and number of bits in control, in the control memory, time switch, is equal to what? We want control memory of these guys. Says how many? We have n slots, so log 2n is the number of bits required to address those slots per second. K, correct, times k, and then how many? 2n. So 2n k times log 2n. This is 2 times 25 times log 2, 128, and this is 5600 basically. Alright, so the next is the number of bits for space switch control memory. Over here, how many lines? N. Slots, it's K. And then, what else? N lines, so log 2 of n, right? Okay. And n lines in those times K times log 2 n capital. And this is in times 25 times log 2 of 16 equals to 1600. So total complexity or total, ignore it, this is the complexity, is equal to 39968. We just sum them and divide basically as we said. Make sense? No, this is actually no, this is total number of bits. Yeah, you can do the calculations, total bits, and find the complexity division over here, but alright? You agree? Okay. So let's continue to the next problem. We have two problems on routing. They are fairly easy, I think, but let's see what you remember. The first problem, I'm going to post this. Okay. So, did you learn about, what routing protocol did you learn? Distance vector, length state, yeah? Okay. So, in the first problem we'll see we have a network as shown in this, and we want for the network given in this figure, give the global distance vector tables like those in 313, where those tables, we have it over here for to see how they look. And then it's when, in three cases, when each node knows only the distances to each at the beginning, meaning. You remember how it like evolves? So the second case is when each node has reported the information preceding step to its immediate neighbors, meaning iteration number 2, and then step B happens in second 3. Okay? That's what we need to do, the distance vector in those cases. If you don't remember many things, or if you want to learn more, a good reference book is the book from Peterson, right? I think this material is from there. Take a look, it's very well written. Okay, let's continue with that. Let's take a look first of all at the reference tables. How do they look? Global view, which means that none of the routers in the network is global. This is God's eye, right? So each of the routers only a vector like this form, only one line of this table. Okay, we have nodes over here. Here we have till G, but it doesn't matter. Okay, so at the beginning we start with some information about our first hop neighbors, and then we keep updating, we keep exchanging messages with our neighbors, and we have, right? Do you agree? Do you remember how algorithm works? Okay, we will see that. So, let's draw at the beginning what is the partial information we have. So that's 3 tables like this. Okay, now to avoid writing the whole table, I have this here. So, first of all, let's see what we can find over here. Distance. Information stored at node A. Distance to reach node A, 0, right? Node B. Oh, I'm sorry. Oh, yeah, I mean, Come out, please. Anybody in the control room? Or maybe like this. Okay, thank you. Yeah, that's fine. So, distance from A to B, 2. Distance from A to C. Initially unknown, we put infinity, right? Distance from A to D, 5. Distance from A to E, same thing, infinity to F, infinity. You got the idea, right? So, in order to continue the same for all the nodes, the first neighbor will have the graph, so it's very easy. Okay, this guy is going to be infinity, 5, infinity, infinity. All the diagonal, 2, infinity, 1, infinity. If you catch any mistakes, please let me know. Infinity, 2, 0, infinity, 1, infinity, infinity, 0, 3, and the last is okay, nothing really special so far. Next round. In the next round, the way to think about it is that node will have information about the neighbors of his first neighbor, first hop 1. So what we can calculate in this case is the optimal distances for distance 2, right? And in the third iteration, we can go up to hop 3, propagation of the messages in the network. Do you agree? Okay, so At the B didn't know about the neighbors of B, A. A knew about, now in the second iteration, he knows about the neighbors of B, so he knows the distance to reach E. What distance? The distance with 2 hops, though, right? So with this, we can go and continue filling up this table, update by using the information from the previous one here. So first of all, the diagonal elements do not change. All right. What we expect to do is to add. In most of the cases, we're going to make them some real number. This is not always the case. We might update some other, some other distance. But over here, for example, the distance from A to B, do have a better option with the information we just got from B. It's 5 plus 2. We don't have, this is 3 hops over here. So the distance from E is 2, remains 2. The distance from A to C, it's 4, right? Information from whom? We got information both from B and D. So calculate what's the minimum distance, right? Perfect. So A to D, that's it. A to E, 3. We know how to get, B, yeah. So we have distance 3 is what? Infinity, perfect. Same logic for here, B to A, B to 2. Okay, right, B to D, with, yeah, B to E, 1, and B to F. 4 versus 5, right? That's the distances we know. 4 versus 5, so it's 4. C to A, 4. C to B is 2. C to D, 2. C to E. We have C to E, it's 3 up here, yes. And then F, 3. Okay, D to A. D to A is, we don't have 6 over here. We can't go. 5. D to B. B is 4. D to C. D to E. D to E, infinity, right? And D to F, it's 5. Okay, E to A, 3. E to B, 1. E to C, 3. D, we can't go, infinity. And then E, 3. F to A. F to B. F to B is 4. F to C, 3. D, 5. And F to E, 3. Okay, that's it. In the next step, we do the same, but now we update based on 3 hops. Now we have the calculations to see if we get some better information, right? So nothing will change really. From A, okay, let me start with this, guys. From A to B. A to B, can I go with 3 steps somewhere? With a better than 2? No. So A to B remains 2. A to C is 4. From 5 from here, we cannot do any round with 3. It's 4. A to D. A, D is 5 versus 6. Now I can go with 6 over here. But I keep 5, which is the B. A to E, 3. And A to F, 7. 6. Okay, B to A. B to A is what? 2. B to C. B to C is 2. B to D, 4. And B to E, 1, and B to F. B to F, we have 5 versus 4. Right? 4. C, A is 4. B. C to C, C to D, C to E and C to F. Alright, and then D to A, DA 5, 5. D to B, DB 4, right? D to C 2. D to E 5 plus 3 8 or 2 2 1 5. D to F is 5. And then E. E to A we can go with 3, right? 1. E to C 3. D is over here, or yeah, 2 2 1 5. B E to F. We could go from here too, but F to A. Sorry, F A. So what's the 2 or 4 plus 3? So it's 6. F B. 4 versus 5, right? 4 3. F to D 5 and F to E 3. Okay, good. Now if you discuss about the algorithm, the distance vector, but I guess with the example you got the idea. You can find some more information first of all in the lecture notes, I think, and Peterson, okay? Over here. Alright. That's, excuse me? Oh, over here. It should be at the optimal point. At, let me see. Yeah. Can you prove that? Correct. That's, yes. Yes, that's right. I like that. The problem is, this is for us solving the problem, the algorithms, right? The algorithm is calculated in every node, irrespective of what's happening in the other. So that's this homework problem, and then we have the last one, which is on Dijkstra's algorithm, right? Link state algorithm, OSPF. Okay, so it's this problem here. Give the steps as 14. Where is the table 314? I'll show you. In the forward search algorithm, the routing database for node A, this guy, shown in figure 360. So over here I want to calculate the of A using the forward search algorithm. Have you seen this guy again? That's a realization of the Dijkstra's algorithm. The Dijkstra is what? It's an algorithm for calculating shortest path, right? So we don't really apply here. It's a district that runs over here. Okay, so show you the algorithm, but first of all I need to show you the what is called, how it looks like. So the table looks like this. As we will see, the algorithm maintains two columns, two lists. One is called confirm, which is confirmed nodes, and these triplets over here. We will see what it is. And the other is the tentative. And here we have a comment for our convenience. Okay, 3 parts. We're going to build the algorithm and see what's the final routing data will look like. Okay, so the algorithm, I need to find. Okay, I found it, guys. Yeah, let's see the algorithm first. We have time. So, question in the problem, right? To build the table. So for building the table, as we said, we need to calculate the extra version and version of the Dijkstra's algorithm called forward sales algorithm. Is the confirmed list with an entry for myself, me A. This 0. Okay. What I didn't tell you is that this format over here is me. Destination, cost, next hop. Good. So we have neighbor, cost. We use the neighbor. We will see what neighbor is. Okay, so first of all, we initialize the list with ourselves. Let's start building the table slowly. At the beginning, we are at A. So we have A, cost is 0. Next hop is, we put, das. No tentative list, nothing. I think it's better not to write the comments over here, but the comments I can give you there, but it's going to take time to write all the comments in this. They are identical to this. Same logic applies, so you have it. Okay. First of all, we said we initialize the confirmed list for myself. This is entry with cost 0. For the node just added to the confirmed list in the previous step, call next and select its link state packet. LS means link state packet, technology introduced by this paper, I think, OSPF. And what it means is basically whatever the distance vector algorithm contains, plus some time to live values sequence number. And the reason for that is we want to keep this algorithm or gets up to date in the sense that we don't want to receive old packets from previous nodes that we already received. We ignore them of the packet. So we want to keep, in order for the protocol to be efficient when it does flooding, okay, and time to live and things like this. The details are in the book, so you can look at that. Okay, this is the LSP. Number 3, for each neighbor, the next, which is the node we just added, right? Calculate the cost to reach the neighbor as the sum of the cost from myself to next and from next to neighbor. Okay. If neighbor is currently on neither the confirmed nor the tentative list, then add neighbor cost next hop to the tentative list, where next hop is the direction I go to reach next direction. Where should I pass through? If neighbor is currently on the tentative list, than the currently listed cost for neighbor, then replace the current entry with neighbor cost, minimize the cost. If you know the distance to another node and you have your tentative list path, update the cost. That's what it means. Where next hop is the direction I go to reach next. And if the tentative list is empty, then we stop. Otherwise, pick the empty from the entry from the lowest cost, move it to the confirmed list and return to step 2. Which means if we have in the tentative list, we just take the one with the minimum cost. We don't care about destination, just the minimum algorithm. So with that, we can go over here. And slowly the table. Okay, so we are at A. The list is empty. We check the LSP of this guy, right? 2 neighbors. It has 2 neighbors, B and D. Okay, what are we going to do next? We're going to put these 2 neighbors in the 10. Why? I mean, we need to go to this step. For each neighbor of next now is this guy. For each neighbor, the cost to reach this neighbor as the sum of the cost from myself to next to neighbor. Okay? So what is next here? For node just added to the confirmed list in the previous step, call the node guy. For each neighbor of this guy, it's confusing because we confuse myself with, it's the same thing. Because it's at the beginning of the algorithm. Then for each neighbor, calculate the cost to reach basically calculate the cost to reach B from B, to reach D from D for us. That's what it means. So what's this cost? The cost will be B, not from E, through B. That's it, right? So the cost 1. That's the cost. And the other cost is what? From A to D is 5, and the cost to reach D through D is 5. D, 5D. Okay, good. In the next step, we go over here. Otherwise, pick the entry from the tentative list with the lowest cost. What is the one with the lowest cost? B. So we add it to the list. Oops. And then we add B1. Perfect. I don't know how I'm going to fit all these guys here, but yeah. So, and then we leave D, 5D. Now, what do we need to do? The neighbors of this guy, of B. We are here. The neighbors are C and D. Okay. C and D, we need to find the distance, the cost to reach the neighbor of C. Okay, so what's this cost? It's 7, and also the other cost is 4. So, you agree? Yeah, so I'm going to put those two guys, those two triplets. One is D4, and the other is C, 7B. Okay, and we can explain why we did that as we said. Then this guy remains the same. Oh, why I put -1? B1B. Okay. Now, what we did over here, though, was we didn't really think, based on the step of the algorithm, but we did the optimization in our mind. We had in the tentative list because we knew only how to get directly, okay? Now we know a path is here. So we updated the value. That's what we did based on the step of the algorithm, to be exact. Okay? Updated the path to go to D. So now we can take the minimum of the two and put it in the list. So now the list becomes A0 minus, dash anyway, B1 and D4B. All right. What is left? C7B. Okay. Continue the same. We go to D. Neighbors of D. It's an E. So what's the cost now to go to C? 5. Perfect. So I'm updating the value over here. C 5 through B. 5 minutes 1. Okay. Do you agree? It's not through D. We are gonna put immediate neighbor. It's B. C5B. And the other is what? C, and we want E, right? E, it's 7. 4 plus 3. So for E, we have E 7, comma B, because this is the next hop. Okay. So the rest remains 3, comma 0 dash B1, B, D4, B. Take the minimum, repeat the process. We didn't miss anything. Oops, sorry guys. 4B, also, which one? C5B. Okay, then we have this guy left. Did I miss it? It doesn't look like. Okay. In the next step now, from C now, we can go to C with cost 5. Okay? I can go to E with cost 6. And here I have 7. So I'm going to update that. E6B. And the rest is the same. And now I have only one left. I take the minimum, put it in the list and the algorithm, okay? And the last step is A0, B, D4, B, C, B, B. If it's confusing, go over the algorithm one more, and I think
the time is 3 o'clock.
It will be clear. It's just, step-by-step questions. All right. Sounds good, guys. Thank you.
And this concludes EE 555 discussion on Wednesday, March 12th, 2014.